Hey guys, in this video I want to talk to you about covalent bonding and the octet rule. So, last video we talked about ionic compounds. Remember, that's a metal and a nonmetal, and when we discuss those we talk about lattice energy. Basically the remainder of this unit is going to be all about covalent bonding. Covalent bonding is when a nonmetal and another nonmetal come together. So we're going to be covering lots of different things with this. We're going to be covering Lewis structures. We're going to be covering polar versus nonpolar, geometry, bond angle, and hybridization. But all I want to talk about right now is just the octet rule. And then I'm going to do a separate video on just Lewis structures for those of you who need it. So the important factor here is to know this octet rule, know where things are coming from so we can do all of these things. Okay, so what the octet rule is basically saying that all atoms want 8 electrons. When you have a covalent compound, you're sharing electrons. The reason why they're sharing these electrons is because all of them want 8. 8 makes them happy, I guess you could say. All right, now there are some exceptions to this rule. One exception is the things that are too small in order to have 8 electrons. Basically, they just can't hold them. They're not big enough. So those are hydrogen, which only needs 2 electrons total, beryllium, which only needs 4 electrons total, and boron, which only needs 6 electrons total. So the reason why they don't need 8 is because, quite frankly, they're not big enough. Now, there's an opposite end of that spectrum, which is something that they will definitely ask on a free response question, and that's called an expanded octet. If you have an expanded octet, that means you can actually hold more than 8 electrons total, but only if you're the central atom. So that's important to note right here. Only if you are the central atom, you can hold more than 8. In the central atom, what that means is basically when you draw your Lewis structure, it's the thing in the center. It's the thing in the middle. That's your central atom. So if that thing can have an expanded octet, and I have electrons left over, then you can tack on some electrons to give him more than 8. He's happy with that. Now we have to be able to, Bo just choked on something. We have to be able to explain why this is the case. Okay, now the reason why we can have an expanded octet, first of all, it's only the things that are in the 3rd energy level down. So if you look at the periodic table, I don't have one here for you. Actually, I do. Hold on. Look, I don't care to get it out. But anyway, if you look at the 3rd energy level, okay, we're talking about nonmetals here. So like phosphorus, sulfur, bromine, iodine, all of that 3rd energy level down. Those are the things who can have an expanded octet if he's the central atom. They don't have to, but if they need to, it's fine. Now, the reason why, our justification, is because it has d orbitals available. You remember where we had the d block, right? Where did that d block start? It started in the 3rd energy level. So basically, this is saying, hey, there's some space, there's some room, we can add some more. It's whatever. Let's just add more electrons to it if we need to. There's space available for that to happen. Now, I put an example down here. Explain why OF5 does not exist, but SF5 does. So this could be a possible free response question and how it pertains to the expanded octet. So the very first thing you'll always have to do is draw the Lewis structure for those, okay? Now, I'm not going to draw the Lewis structure because we already know our justification, but if I were to do so, OF5 would not be a Lewis structure that could happen. SF5 does happen, though. It's able to be drawn. The reason why, S is in the 3rd energy level, but oxygen is only in the 2nd energy level. S can have more than 8 electrons surrounding the central atom because it has an expanded octet, because it has d orbitals available. So that's what you're going to be talking about with your justifications dealing with expanded octets. And when you start drawing these in Lewis structure form, that'll make more sense to you. Now, the very last thing I want to talk about in this little video is about multiple bonds, okay? Multiple bonds meaning double bonds, triple bonds. Those can only happen between CNOPs, C CNOPS. CNOPS is carbon, nitrogen, oxygen, phosphorus, and sulfur. You therefore cannot have a double bond between nitrogen and bromine. Do you see bromine on CNOPS? No. Only CNOPS. More than one CNOPS coming together can have multiple bonds if needed. Okay? Now, how they can ask questions dealing with this? Well, single bonds are the longest bond and the weakest bond. Triple bonds, however, are the shortest bond and the strongest bond. So let me show you what I'm talking about here. Let's say I have X here, and there's a single bond, and it's bonded to another X. We're just going to say that the X are the atoms, and the line there is the bond, okay? The question is, how many electrons do I have between these two atoms? And the answer to that is 2. I have 2 electrons. Now, those 2 electrons are going to be attracted to the positive nucleus. Negative electrons, positive nucleus. What it's going to do is squeeze those little atoms close together. Now, that's only 2 electrons holding to both of these nuclei. What if I have a double bond? So, I have a double bond. Here's X, a double bond. Look at my pretty straight lines. And another X, right? Well, now I don't have 2 electrons holding on to the nuclei. I have 4 electrons holding on to the nuclei. So because I've done something called increasing electron density, you see that sentence at the very bottom. If I increase electron density, meaning I add more electrons in the middle, what that's going to do is pull those atoms closer together, because the nucleus is positive, it's going to be attracted to that. And if I'm pulling the nucleus closer together, then that's going to make my bond shorter. So if I add a triple bond, 1, 2, 3 little bonds, that's how many electrons in between them? That's 6. Now, instead of just 4 electrons holding on to these 2 atoms, I have 6 electrons holding on to those 2 atoms. So even more so, those atoms are going to be pulled closer together and shorten the bond length. Now think about this conceptually. If I have a really, really short bond, it's going to be a lot harder to break that bond, right? So therefore, the shorter the bond length, the harder it is to break the bond, meaning that its bond energy or bond strength increases. So relationship, electron density increases. That means I'm adding more electrons in the center to bond those atoms together. Bond length decreases, and bond energy or bond strength increases. Okay, that is our relationship there. So you might have to compare one thing that has all single bonds versus something else that has double bonds and discuss the strength and the length according to that. One other thing you'll have to be able to do with this multiple bond stuff, and that is something that is very easy to tackle. And this is something called sigma pi bonds, okay? They will give you a structure, and let's just say, like, this is my structure. I'm just gonna throw something at me here that's probably not even valid. 1, 2, 3, put an X there, and let's do another X there, another X here, let's do a double bond there, and let's do a single bond. Yep, that can't happen, but let's just say it can, okay? Now, they will give you some huge organic structure. Now, no, you do not need to know organic for AP Chem, but they will try to throw something scary at you when it's a really easy question. So they're going to give you some elaborate structure like this, okay? And they will ask you the question, how many sigma and how many pi bonds that are present in that structure? Here's what you do. If I have a single bond, that is classified as a sigma bond. Now, sigma is the lowercase sigma. That is it. We're not talking about uppercase. I'm sorry, I don't know Greek. But the Greek alphabet, you might be thinking of that as sigma. Okay, it's not that what we're talking about. We're talking about the lowercase version, if that's a thing. And so that is your sigma. So single bonds only get sigma bonds. Double bonds get a sigma pi bond. So you see how the first line is sigma, the second line is pi. And my third gets a sigma pi pi. So my first line is a sigma, my second line is a pi, and my third line is a pi as well. So again, the question is asking how many sigma bonds, how many pi bonds. All you do is you go through here and I say, okay, let's count my sigmas. Well, I have 1, 2, 3, 4, 5, 6 sigma bonds here. So I have 6, that's a 6 sigma, bonds present here. And what I just noticed is when I do the computer, I think I do a check mark correctly. Oh, no, I think it's still backwards. Oh well, that's how I do it. Now let's ask the question, how many pi bonds do I have present? So we'll do pi in green. I have 1 pi bond, 2 pi bonds, 3, and 4 pi bonds present there. So my answer would be 6 sigma and 4 pi bonds. And that is all you need to know. I hope this was helpful. I hope that you learned something or reviewed something, and this is all coming pretty easily to you. Real quick, I got to talk to you about something that was really cool that I did my first couple of years teaching AP. First couple of years, we made like our own like little chemistry sorority or fraternity, whatever you want to call it. And we had shirts called Sigma Pi Pi. That's what we called ourselves. And we were Sigma Pi Pi, the closest bonded students at HTHS. Get it? Yeah, it's cool, isn't it?